Today's lesson in Chapter 16, we're going to be talking about probability. And in your guided notes, this starts with page 3 of your Chapter 16 notes packet. So you've studied probability since elementary school, I'm hoping. And what the definition of probability is that it's a ratio, the ratio of the number of successes in whatever event you're trying to cover divided by the total possible outcomes. We usually talk about probability and maybe rolling a certain number on a dice or maybe flipping a coin. But the definition of probability is that it's a fraction. And the numerator is always less than or equal than the denominator. So if you always keep in mind that probability is somewhere between 0 and 1, it could be equal to 0, which means there would be no probability of it occurring, or it could not occur. Or if your probability is equal to 1, that means that there's 100% chance that it will occur. But usually the probability is somewhere in between 0 and 1. It's often represented as a fraction, but sometimes you can represent it as a decimal or a percent. Fraction, decimal, or percent. Like when we looked at the bell curve in the last chapter, we represented the probability in many different ways. So there are going to be 4 types of probability that we're going to be covering today. So the 4 types of probability are listed, 2 of them on this page. The first one is called theoretical probability, and this is just in theory what would happen. It's not actually happening, but what would probably happen, theoretical probability. What that means, it's the number of ways that an event can occur divided by the number of possible outcomes when each outcome is equally likely to occur. Well, that's a lot of words, but you've done this for many, many years, and it just means this. For example, if you wanted to, at random, choose a month that begins with the letter J from the months of the year, you know that January, June, and July, there are 3 months that begin with the letter J, and the months of the year, there are 12 months in the year. So if you were randomly to choose a month out of the month of the year, what's the probability that it'll begin with the letter J? The probability is 3 out of 12, and you don't have to reduce. And that's theoretically. When you actually perform this action, if you were given a hat that has all of the months in the year and you were to choose a month out of the year, then you either are going to choose one or you're not. But this is just theoretically, and we'll talk about the other kind down at the bottom of the page. Now, example 2 is a lot harder than example 1. There are a couple of different ways that you can do this problem. So first of all, you have to read these problems a couple times to see what they're actually asking you. And what they're actually asking you on example 2 is, after arranging the letters in the word tomato. So we're going to arrange all the letters in the word tomato. And if you remember from yesterday, all of the different number of arrangements that we could get is, you can count up how many letters there are in the word. There are 6 letters in the word. So it would be 6 factorial. But then you have to divide out the duplicate letters because there are 2 T's and 2 O's. So what we have to calculate is how many different ways we can arrange the letter tomato. Because what we're asked is, what's the probability that when we arrange these letters, that this word, it's not a real word, but this arrangement of letters will start with a T and end with a T. So we have to calculate how many different ways the word tomato could start and end with a T. So the numerator here is the number of ways that the event can occur. So how many different ways How many different ways does the word tomato start and begin with a letter T? So the top is number of ways start and end with a T. So that's the number of ways that an event could occur, and divided by the number of possible outcomes. Well, the number of possible outcomes, if you take all of the letters in tomato and arrange them, that's what the possible outcomes. So the number of ways to arrange tomato. So what you have to do now to figure out how many different ways to start and end the letters of tomato with a T is, if you remember yesterday, I put a little dash for each letter of the word tomato, T-O-M-A-T-O. I've got 6 dashes. And what we want to do is figure out how many different ways you can arrange these letters to start and end with a T. Well, if it starts with a T, how many different ways? We have 2 different letters we could choose from. So we're going to put the number 2 here because we could either choose this T or this T and put it in the first position. So let's say we chose that T. Well, we have 5 letters left, but the other constraint we have is that the last letter also has to start with a T. So once we get rid of that first T, we only have 1 choice of letters to put in the last position. So there's our constraint, start and end with a letter T, 2 different ways, 1 different way. And then we have 4 blanks left to arrange those 4 letters. So we have a possibility of 4 letters left, 3 letters left, 2 letters left, and 1 letter left. And then you have to remember that because tomato has duplicate T's and duplicate O's, you have to divide this whole thing out by the duplicate T's, 2 factorial, the duplicate O's, another 2 factorial. So this numerator is the number of ways that tomato could start and end with a T. Now the denominator, how many different ways could you arrange tomato? So you're going to divide this by, and if you remember from yesterday, the number of ways you could arrange tomato is because there are 6 letters, it's 6 factorial, but there are 2 duplicate T's and duplicate O's. So the number of ways to start and end with a T. Here's the starting T, here's the ending T, but the duplicates have to be considered, and the number of ways to arrange tomato. Well, this is really a complex fraction, and if you want to consider like this, the denominator, the LCD is 2 factorial, 2 factorial, we can really just cancel these out as part of the complex fraction reduction. So what we're left with is 2 times 4 times 3 times 2 times 1, which is 2 times 4 is 8, 6 times 8 is 48, and divided that by 6 factorial. So let's see what 6 factorial is. It's 720. So 48 over 720 would be the probability that the arrangement, if you just picked a random arrangement, it would be starting and ending with a T. And if you wanted to reduce that down, your calculator can do that for you. Just 48 divided by 720 math frac. Whoops. And 1 over 15 would be reduced, but you don't have to reduce probability. You can just leave it like that if you want. And that's a harder way of doing it, but there's an easier way. Sometimes you kind of have to think about it in these terms, but if you want to really think about it another way, you can say, well, there's a probability with the word and in it, and an and in probability means you're going to multiply the 2 probabilities. So what's the probability that an arrangement is going to begin with the letter T? Well, there are 2 T's in the word tomato, so you have two chances out of 6 total letters that it will start with a T. And then, what's the chance that after you take that T away, that it's going to end with the letter T? Well, you only have 1 T left, but you only have 5 letters left to choose from. So 2 over 6, the chance of it beginning with a T, times the chance of it ending with the letter T, multiplying the probabilities because it's and, will give you 2 out of 30. And if you wanted to reduce 2 out of 30 down, it reduces down to 1 over 15, which is the same thing as this, but with a lot less work. So you can think about it in either way. I just wanted to show you a couple different ways to do that. In example 3, you pick 3 different numbers from the numbers 1 through 50 in a lottery. So I'm not sure. Sometimes if you go to a diner, you'll see the 50 numbers in the lottery up on display, and then you can see how they're picking them. So let's say you're trying to pick 3 numbers from the lottery. What's your probability of choosing all 3 winning numbers? Well, let's choose the first number. What's your probability that you're going to choose the first winning number? Well, there are 3 winning numbers. So you have 3 chances out of 50 numbers that you're going to choose the first winning number. Now, after you've chosen the first winning number, you're going to try to choose the second winning number. Well, you've already chosen 1 number out of the 50, so you're left with 2 winning numbers left in the pool, but there are only 49 numbers left. And then after you've chosen the second winning number, there's only 1 winning number left, but there are only 48 numbers left to choose from. So if you wanted to multiply those 3 probabilities together, you could do it that way, and you could get a nice, great, big, giant fraction. Or an easier way, and like I said, you can just put those in your calculator and figure out what that fraction, what it would be. Or you can say, I am choosing 3 numbers. I wanted to choose all 3 winning numbers out of the 3 that are in the 50. So that's my probability of choosing all 3 winning numbers divided by I'm going to be choosing 3 numbers out of the 50. Those are the different numbers of ways I could choose the 50. It doesn't matter what order you choose lottery numbers in, as long as you've chosen them. But there are 3 numbers to choose from, 3 winning numbers to choose from, and if you choose all 3 of them, there's your probability. So what this turns out to be, 3C3 is equal to 1. I know that just because I remember that when those 2 numbers are the same, it's equal to 1. Whoops, I'm sorry. I've got this written backwards. The bigger number has to go on the left. 50 has to go on the left. And the 3 has to go on the right. Sorry about that. Remember always to put the larger number here. So let's see what 50C3 is. 50, math, PRB, option 3, 3. 50C3 is 19,600. So there's 1 chance in 19,600 that you'll choose 3 winning numbers from 50. Or if you wanted to figure out this, 3 times 2 is 6, and then 6 goes in the numerator, and 50 times 49 times 48 is 117,600. And if you reduced each one of these down by 6, 117,600 divides by 6 evenly, so that would be 1 over 19,600. So there's 2 different ways to get these probability questions, and you could either do it this way or this way, whatever makes most sense to you. Okay, the next thing we're going to talk about is empirical. So this is type number 2. If type number 1 was theoretical, type number 2 is empirical probability. So the empirical probability is the probability of an event by observing the data or the results of an experiment. It's an estimate on a theoretical probability based on a large number of trials. So experimental means you're going to just do an experiment and you are going to actually calculate what happened. All right, it's not theoretical, but it's an actual number. So let's say Miles was a student in my class last year. If Miles takes 50 shots from a free throw line in basketball and he makes 28 baskets, what's his probability of making a free throw? Well, he actually shot 28 baskets. He actually made 28 baskets and he shot 50. So his empirical probability, because that actually happened, it's 28 out of 50. Maybe he has a better chance based on some other variables. He has a better chance of making a basket, but what actually during this trial happened, it was 28 out of 50. So it actually happened versus what could theoretically happen. Here's a third type of probability called geometric probability, and that is just you have to know the geometry, you have to know the area formula for various shapes. And so what you're going to do is you're going to divide the area. So make sure you know area formulas, area of a triangle, area of a square, rectangle, and a circle. And you're going to divide the area of an inner region by an outer region to get the probability that maybe something will land in the shaded region. So for example, let's say you have a dartboard. You have two dartboards. One looks like this. I know it doesn't really look like one. But if you have a dartboard that looks like this and you randomly throw darts at that target, what's the probability that you're going to hit the shaded area? Well, it's the area of a triangle divided by the area of the square. So the area of the triangle is 1/2 base times height, so 3 times 2 is 6, and 1/2 of 6 is 3. And the area of the outer square is 6 times 6 is 36. So you have a 3 in 36 chance of hitting that shaded area, or 1 in 12. In part B, you have a rectangle here and a circle inside, and you have to remember the area of a circle is pi r squared. So pi r squared divided by length times width would be the circle divided by the rectangle. The radius is 2. 2 squared is 4. So you have 4 pi for the circle, and 5 times 8 is 40. So 4 pi over 40 would be that, or you can reduce that down and call it pi over 10 chance that it'll land in there. So that's just a quick geometric probability. And then the fourth thing, sometimes you'll have probability of more than one event. We talked about that on the previous page, but if you have 2 events or more occurring at the same time, we say the probability of it is A and B, and I mentioned the probability of A and B, and you're going to multiply those probabilities. We already did that on the previous page. So for example, if you have a die and a coin, and you roll the dice and flip the coin, what's the probability of getting 3 on the die and heads when you flip the coin? Well, to get a 6 or to get a 3 on the dice, you have a 1 in 6 chance, and to get heads on the coin, you get a 1 in 2 chance. And the probability of getting a 3, and is the key word. When you see the and word and, it means multiply the probability. So 1/6 times 1/2 is you have a 1 in 12 chance of getting that. But on the other hand, if you have 2 events that are exclusive of the other, one could happen or the other one, not both, but one or the other one, then if you see the word or in probability, that means you add the probabilities. So if you roll a dice and flip the coin, what's the probability that you'll either get 3 on the die or heads? Well, or is the key word, or means and. And if you add 1/6 to 1/2, you'll get 2/3 if you reduce it down. So these two last examples, what if you pick a card from a deck of cards? What's the probability that you'll choose an ace or a king? Okay, so what's the probability that you'll choose an ace? Well, there are 4 aces in a deck of cards out of 52. And then after you choose your ace, then you want to see what the probability of, or not afterwards, but or a king. Or means you're going to add probabilities. So whenever you see or, say, okay, I'm going to add the probabilities together. So what's the probability of choosing a king out of a deck of cards? Well, there are 4 kings, and there are 52 cards in a deck. I'm not sure if everybody knows this, but 52 cards in a deck of cards. So an ace or a king, you would have an 8 out of 52 chance of picking one or the other. Or another way of looking at it is you can say, well, together there are 8 aces and kings, and then I'm choosing one of those aces and kings, so I have an eight of those cards out of a total of 52. So you could just jump to this conclusion if you know that there are a total of 4 aces and kings in the deck. But this is the other logical way. Okay, the last example here is, what if I pick 2 cards from a deck of cards, and what is the probability that I'll choose an ace and a king? Well, here's the key word, and it's in that order. So you could do this a couple of different ways, but you have to remember that and means multiply probabilities. So if I choose one card out of the deck of the cards, and I choose, what's my probability of choosing an ace first? I have a 4 in 52 chance of choosing an ace. Now I'm going to choose a second card out of the deck. But once I've chosen the first card out of the deck, then there are only 51 cards left. And I want to choose, what's the probability of choosing a king out of those 51? Well, there are still 4 kings left because I chose, my chances of choosing an ace were 4 out of how many cards? My chances of choosing a king were 4 out of the remaining 51. So you're just going to have to multiply. 4 times 4 is 16, and 52 times 51 is a pretty big number. 52 times 51 is 2652. 2652. So I have 16 chances out of 2652 to choose an ace and then a king because it's a multiplication problem. And that's it for today. I'll see you tomorrow.